Alright, so we're going to go ahead and start logarithmic functions, and these functions right here are just your basic logarithmic functions with different bases. So this is always kind of what your graph is going to look like when you have a log function. So let's just start out with what is a log and why we need them. So if we look at this right here, 2 to what power gives me 4? That's something I can think about, and it's pretty easy to figure out that question mark would have to be 2. Okay, so I would have to take 2 and raise it to the second power to get 4. Same thing here. 2 to what power gives me 8? Well, question mark would have to be 3. 2 to the third power would give me 8. But our last one, 2 to what power gives me 7? I can't figure that out exactly unless I have logs. I can guess that since 7 is between 4 and 8, then my exponent is going to be somewhere between 2 and 3. But I can't figure out what exactly this is until I use logs. So let's go ahead and define what a logarithmic function is. If I have x equals b to the y power, if x equals b to the y, then the logarithmic form of that, so logs and exponentials are really, really closely related. So if I have this as an exponent, then I can rewrite this as a log. And the way that I would rewrite that is log base b, and then the x's and the y's kind of switch places. So right here, b was beside the y, and so now it's going to be an x right here equals y. And so I would say this as log base b of x equals y. And so this is how I would go back and forth between logs and exponents. And so there are some important things that I need to remember about logs. The first thing is exactly what I just said. A log is just an exponent. That's all a log is. It's just an exponent. The second thing you need to remember, and we'll go over this a little bit later when we get to inverses, our unit on inverses, but the second thing is logs and exponentials are inverses. The third thing that I need to remember is, if we remember back to our exponentials that we talked about the other day, we said this base could never be a 1, because if it is, it'll be a constant function. So it's the same reason holds true in the log form. So we can never have our base to be 1. It can't be 1. And then we said that this number right here, we saw when we plugged in some positive exponents and some negative exponents, we saw that this number right here was just going to either be a number that got really, really big and shot up, or it got really, really small and got close to 0, but never actually was 0 or negative. So this x was always greater than 0, which means it was positive in our exponential. So same thing's going to be true with our log form. So the x has to be greater than 0 in a log form. Now, let's just look at rewriting these in exponential form. So these are all logs, and I want to rewrite it as an exponent. So the way I'm going to do that is, there's a little saying that I do. I always circle the base. Okay, the base is going to be raised to the power 5. So I'm going to draw an arrow over to 5. Now, the little saying that I do is, this little circle is like a shell. And this little arrow is like a snail that comes out of its shell, and it eats the 5. So whenever I say shell snail, I just mean rewrite it as an exponent. Okay? So I'm going to shell snail, and that's going to tell me that 2 to the 5th equals 32. And if you test that out, it should give you something that's true. So 2 to the 5th equals 32. 2 raised to the 5th does give me 32. Okay? Now, same thing with number 2. I'm going to shell snail. So this is going to be 3 to the 3rd equals 27. That's a true statement. All right, and then C, this is going to be 4 to the 1/2 equals 2. Another way that you might see somebody write this would be like this. Since the 1/2 power really just represents a square root, somebody could, or you could see it written as the square root of 4 equals 2. Now, last one, this is just a log of 1 over 100. There's no base that I can see here. And so if I don't have a base, the base is understood to be 10. Anytime there's no base in a log, it's just going to be 10. And so then I'm going to shell snail. And so that would be 10 to the negative 2 equals 1 over 100. All right, now let's go the opposite way. So these are exponents, and I want to write them as a log. So I'm going to do the same thing. I'm going to shell snail. So I'm going to shell and then snail. And so when I do that and write it as a log, log base the shell, that's always going to be the base. So 6 of 1 over 36 equals negative 2. All right, same thing here. I'm going to shell snail. So this is log base 8 of 64 equals 2. All right, number 3. I'm going to shell snail. So this would be log base 10 of 1 over 1,000 equals negative 3. Now, the way that I would probably see that written most of the time is without that base 10, since it's understood to be 10 if I have no base. So this is probably how I would see it written in the blue. And then number 4, I'm going to shell snail. So this is going to be 2 to the 1/4 equals negative 2. No, I'm writing this as a log. So this is not going to be that. This is going to be log base 2 of 1 over 4 equals negative 2. Sorry about that. All right, so then these are all of our exponentials as logs. Now, we want to evaluate using the definition of a log and the properties. So what that means is I want to actually find what this is. Okay, so this is going to equal something out here. It's going to equal a number, and I want to find that number. Now, what this is kind of asking, and some of these you can do in your head, but there's also another way that I'm going to show you how to do these. This is really saying 3 to some power should give me 81. So 3 to some power gives me 81. And so you can think about it and you can figure it out without using a calculator. Or the other way that you can do it with a calculator is by what I like to call doing log tall. And when I say log tall, I mean the number that's actually larger. Not the number that is numerically in value bigger, but the number that the font is bigger on. So this is going to be log of 81 divided by the small number, the subscript number, log 3. And so some of you may have been able to figure out that 3 to the 4th power gives me 81. But if you can't, then you can do this, log tall divided by log small. And so that would be 4. And so then when you rewrite, if you went back and you said, okay, I know that equals 4. If I rewrote this as an exponent, shell snail, then 3 to the 4th should give me 81. So you can check your answer. Now, number 2 is a little bit different. If you see an LN is just a log with a special base. And so an LN is just going to be log base E. If you ever see LN, then this is just telling me that the base of the log is E. And so when I see LN, a lot of times I'll go ahead and rewrite LN as log base E. Okay, so I just went and changed my LN to log base E. And then I've got the rest of my problem, e to the 2x. Now, this is saying, if I shell snailed, e to some power should give me e to the 2x. So e to some power should give me what's left there, e to the 2x. And so the only thing that this question mark could be is 2x. So 2x is my answer there. And that looks a little bit weird, and if you don't get that one, that's okay. We're going to come back to problems like that whenever we do solving equations. But it should be 2x. Number 3, this is a normal one. So I'm going to say, okay, 4 to what power gives me 1 over 64? That one may be a little harder to think about and figure out. So I'm going to do log of the taller number, the visually tall number, divided by log small. So log tall divided log small. And so then I'm just going to plug that in. So log of 1 over 64 divided by log of 4 And so then that should give me negative 3. So my answer is negative 3. Okay, same thing here. The base is 10, so I would do log tall, log of 1/10 divided by log small, log 10. And so then log of 1/10 divided by log 10 would give me a negative 1. All right, we'll combine some of our properties and do some problems like this. So, number 5, this is asking, this first log is saying 2 to what power gives me 4? Okay, and 2 to the second power we know gives us 4. So that one shouldn't be too hard to figure out in your head. Plus, you may need to do log tall, log small on this. If you do, that's fine. You could have done log tall, log small here. Either way, they'll give you the right answer. So I'm going to do, to find this one, log tall divided by log small. So log 27 divided by log 3. And so that gives me 3. And so 2 plus 3 would then give me 5. Alright, number 6. 16 to what power gives me 4? You may be able to think, okay, well that would be the square root of 16, so the answer is 1/2. If not, you can just do log tall divided by log small. So I'm going to do log tall divided by log small. And so that should be 0.5, or I'm going to write that as 1/2, plus, same thing here, log 3 divided by log 9. And so then that should give me 1/2. And then minus log base 8, 2, that's just going to be log tall divided by log small, so log 2 divided by log 8. And so then that gives me, as a fraction, I know that's going to be 1/3. So then 1/3 goes there. And so then 1/2 plus 1 would combine to give me 1. And 1 minus 1/3 would be 2/3. And so that's my answer. Alright, now we're going to look at logarithms as functions. So I'm going to go on to characteristics of logarithmic functions. And so we're just going to look at the few things that you should be able to find. The 3 things are domain, vertical asymptotes, and x-intercepts. And so you can see right here, this is just the graph of the simple function log x. So this is base 10, since there's no base there. And you can see that the graph gets close to the y-axis but never really crosses it, and that's because there's an asymptote there. You can kind of see what the x-intercept should be, and the last thing you should, or the first thing you should be able to find is the domain. So the domain, to do that, since we know we cannot take the log of a negative number or 0, can't take the log of 0 or a negative, then what I'm going to do to find the domain is I know that these numbers that I plug in have to be positive. And so what I'm going to do is set whatever's inside greater than 0. Greater than 0. Now, the vertical asymptote is just going to be whatever makes the inside equal 0. So I'm going to take the inside and set it equal to 0. And then the x-intercept, I'm going to solve the same way I always have by plugging 0 in for y and then solving for x. And so we're going to go ahead and do a couple of these problems. So this one's just a real simple one. And so I'm going to start by finding the domain. Now, if I just have log base 4 of x, it's understood that the x is kind of what's inside the log. Okay, if there's other stuff inside the log, they'll group it with parentheses, kind of like this one. Okay, the x plus 5 is inside the log. So to find the domain, I'm going to set what's inside the log greater than 0. So I'm going to set x greater than 0. And since there's nothing left for me to do there to solve, I'm going to go ahead and say the domain of my function is x would belong to, since it's greater than 0, it would be 0 to positive infinity. And I would not have a bracket here because this is not or equal to. Remember, we don't want it to equal 0 because I can't plug 0 in right there into a log. So then here's my domain. Now the vertical asymptote, I'm just going to take what's inside and set it equal to 0. And since there's nothing left to do, the vertical asymptote is just going to be x equals 0. And now you'll notice that every time these numbers should match. These numbers should match. And now for x-intercept, I'm going to plug 0 in for y. F of x is like y, so I'm going to have 0 equals log base 4 of x. Now, we're going to use what we just did to help us solve this. So I'm going to shell snail. And when I shell snail, you'll see that I get to solve for x. So I'm going to shell snail. So 4 to the 0 equals x. Alright, so 4 to the 0, anything to the 0 power, no matter what it is just going to be 1. So 4 to the 0 is 1. So 1 equals x, and if I write this as a coordinate, this would be 1, 0. So now I'm going to plot all of that stuff on my graph. So the vertical asymptote is going to be 0. The x-intercept is at 1, 0 right there. And so then my domain is going to be from 0 to positive infinity. That tells me it's going to keep going out somewhere like this. And then if you look at all of our graphs, let's go back to the very beginning and look at the graphs. These functions that flip, we're not going to look at those right now. We're just going to look at these functions. These are my regular functions. So a logarithmic function is always going to have that basic shape. So it's going to get really close to the asymptote and then shoot out and up slightly. So this is what my graph should look like. This is going to shoot down right here, go down, and up and out to that side. Alright, let's see number 2, the domain. I don't want my inside to be negative or 0. So I want x plus 5 to be greater than 0. So x should be greater than negative 5. That means the domain is x has to belong to the set from negative 5 to positive infinity. The vertical asymptote is going to end up being, I set x plus 5 equal to 0, so x equals negative 5. So again, these numbers should match. And then to find my x-intercept, I'm going to say 0 equals x, not x, but log base 2. So log base 2 of x plus 5. And now, since I've got to, in order to get rid of this 5, I can't go ahead and subtract it over to in the beginning. So we can't move stuff outside parentheses if it's inside that log. And so the way that I'm going to do this and solve is by shell snail. So 2 to the 0 equals x plus 5. And we said 2 to the 0 is just 1. So 2 to the 0 is 1, so 1 equals x plus 5. And when I subtract 5, x is going to be negative 4, and so my intercept is negative 4, 0. So now when I graph all of this, this is going to give me the vertical asymptote at negative 5. 1, 2, 3, 4. So back here. And then my intercept is at negative 4. And then the graph, the basic graph looks the same. So then it's just scooted to the, and you can think about this as one of your transformations. This one wasn't scooted at all, but this one takes the function and scoots it to the left 5. So that's what we did right here, and that's what my function looks like. Alright, number 3, I'm going to change this example just a little bit, because there's one on your homework that I'm going to give you that you're probably not going to know how to do unless I do an example, and I'm going to change this to minus. Okay, let me make sure this is going to work. So, alright, that should work. Okay, so for the domain, even though there's other stuff in this function right here, I still want what's inside the log, and the 1 minus x is the only thing that's inside the log. So that's the only thing that I want to be greater than 0. So I'm going to solve this. I'm going to solve by subtracting 1. That'll give me negative x is greater than negative 1. And then I'm going to divide by negative 1. And so when I do that, x has got to be, and if you remember back to your rules in algebra, if you divide by a negative when you have an inequality, what does that do to the alligator mouth? It just flips it. So it's going to be less than now. So negative 1 divided by negative 1 is just a positive 1. And so my domain is x has to be less than negative, or less than 1 now. So I would say d of f, and I would go from negative infinity up to 1. I want everything to be less than 1, so it would be from negative infinity to 1. Now, vertical asymptote, I'm going to set what's inside equal to 0. So negative x equals negative 1, divide by a negative, and x equals 1. So that's the vertical asymptote. And then x-intercept, I'm going to let y be 0. So I'm just going to say 0 equals, and then this is log base 6, 1 minus x minus 3. Now, in order to shell snail, I cannot go ahead and shell snail with this 3 out here. I need to get the log by itself. So the log and what's inside needs to be alone. So I'm going to go ahead and get rid of that 3 first. So to do that, I'm going to add it over. So this would be 3 equals log base 6 of 1 minus x. And so then I can shell snail and say 6 to the third equals 1 minus x. Now that's going to be a big number. So 6 raised to the third is just going to give me 216. So I would say 216 equals 1 minus x. To solve for x, I'm going to subtract 1. So this would be 215 equals negative x. And when I divide by a negative, x is going to end up giving me a negative 215. So my x-intercept is a really big number, negative 215, comma, 0. Now, the way that I would plot that and graph it is going to be a little bit different. I'm going to graph the asymptote first. So at 1 right here, I've got an asymptote. Now my x-intercept, I'm going to scale this a little bit. I'm going to make this negative 50, negative 100, negative 150, negative 200, and then finally negative 250. So I'm just going to scale it. So my x-intercept is going to be at negative 215. So that's going to be somewhere right here-ish. And so then, because my domain is going in the negative direction, that tells me I don't want anything on this side of the asymptote. I want it to be everything from negative infinity to 1. So what this does, what the negative beside the x on the inside does, is it kind of just takes our function from here. If it looks like this, and the x is positive, if I have a negative, if I have a negative in front of the x, it just flips it over the asymptote. So instead of it going this way, it's going to go this way. I'm going to flip that back because that was not our function. So flip left, right. Alright, so over here, when I draw my graph, it's going to go and shoot down like this right here. And then up, and I'm going to draw this in red actually. So it's going to shoot down like this, and up and out to that side. And so this is what my log function would look like. And this one's a weird one. Most of the ones on your sheet are not like that. Last one, let's do an ln. So number 4, the domain, I'm going to do the exact same way. So I'm going to take x over 2 and set it greater than 0. ln, you're going to do the exact same way as we do a regular log. So I'm going to go ahead and take this 2 and get rid of it. And so to get rid of it, I'm dividing. I need to multiply to get rid of it. So this is going to be x has to be greater than 0 times 2 is just 0. So domain is x belongs to 0 to positive infinity. So I know my graph is going to go out to the right, somewhere out here. Vertical asymptote, I just take x over 2 and set it equal to 0. So x equals, when I multiply the 2 over, 0. And then my x-intercept, I'm going to let y be 0. And so that's what I've got. Now, the base of an ln, we already said base of an ln is just e. This is just log base e. So I'm just going to make that log base e. And so when I solve for my x-intercept, I can go ahead and shell snail. So e to the 0 equals x over 2. Now remember, e is just that number, 2.7 blah blah blah. So e to the 0 is just going to be 1. Any number to the 0 is 1. And when I multiply that 2 over, that would mean x equals 2. So the point is going to be 2, 0. And so I'm going to go put all of this stuff on my graph. So right here at x equals 0, there's an asymptote. At 2, 0, there's my intercept. And then this graph isn't flipped or anything, so it's just going to look like a normal graph and have that same shape, that basic shape. And that is it.